Physicists believe they understand quite well how the universe works on large scales. The key assumption to this model for the universe is the cosmological principle, according to which the universe is approximately the same everywhere. But increasingly more observations show that the universe just isn't the same everywhere. What are those observations? Why are they a problem? 2 years ago, I told you about a paper by Zubair Zakar and his colleagues that showed if one analyzes the supernovae data correctly, without assuming that the cosmological principle holds on too short distances, then the evidence for dark energy disappears. That paper has been almost entirely ignored by other scientists. Check out my earlier video for more about that. Today I want to tell you about another problem with the cosmological principle. As I said, one can calculate the scale from which on it should be valid from the standard model of cosmology. Beyond that scale, the universe should look pretty much the same everywhere. This means in particular there shouldn't be any clumps of matter on scales larger than about 1 billion light-years. But astrophysicists keep on finding those.
Astronomers are always looking for the most distant galaxies, the most energetic stellar explosions, and the most massive stars. But what about the biggest cosmic walls? Hello, I'm Ian O'Neill, space producer for Discovery News, and I want you to imagine the biggest collection of galaxies possible. Now double it. No, triple it. Can you see it? Well, yeah, that's a giant galactic wall. Well, okay, these walls aren't made of bricks and mortar, but they are walls of galaxies cemented together by dark matter. They are the biggest structures in the universe that we know of, and they are huge. And perhaps the most famous galactic wall is the Sloan Great Wall that was discovered by the Sloan Digital Sky Survey, or SDSS, in 2003. It's basically a huge collection of galaxies around 1 billion light-years from Earth, spanning over 1.4 billion light-years across. Although impressive, the Sloan Great Wall is no longer the biggest. It remains the most famous. Since 2003, bigger galaxy walls have been detected, but this year the biggest wall of all has been claimed. When studying a collection of distant galaxies between 4.5 and 6.4 billion light-years away, astronomers realized that over 800 of them occupy the same cosmic filament, a volume 10 times that of the Sloan Great Wall. They called it the BOSS Great Wall, after the Baryon Oscillation Spectroscopic Survey, a project also run by the SDSS. BOSS is designed to study the distribution of galaxies throughout the cosmos in an effort to understand how fast the universe is expanding and how galaxies move in relation to one another. Although impressive, the Great Walls may not actually be the greatest of them all.
Sometimes even massive structures are hidden from view. Our own Milky Way's dusty center obscures whatever's behind it, an area of the sky above the South Pole that has been dubbed the zone of avoidance. Which is funny, because the zone of avoidance is what I call anywhere with people during the pandemic. Some cosmographers were undaunted by the zone, though, and they pulled out some clever tricks to peer into it. The universe is expanding, which means on the whole, galaxies should be moving away from us at a constant rate. Using a catalog of motions and distances of 18,000 galaxies called Cosmic Flows 3, the scientists noticed that some galaxies were moving faster or slower than expected, and seemed to be drawn to something in the middle, something hidden in the zone of avoidance, something big. Computer models revealed a wall made up of thousands of galaxies at least 600 million light-years deep and 1.4 billion light-years across, forming a bow shape over the southern hemisphere's sky. They have creatively dubbed this wall-like structure above the South Pole the South Pole Wall. And not only is it enormous, it's one of the top 10 biggest structures ever observed, it's also relatively close. It's 500 million light-years away, twice as close as a similarly sized structure called the Sloan Great Wall. It's large enough and close enough that it actually affects the velocity of our own galaxy, contributing about 40 kilometers per second to the movement of the Milky Way. The South Pole Wall could in fact be even bigger than we think. Its curved shape allowed for a lot of it to fit within the Cosmic Flows 3 view, but it's possible that the wall extends beyond what we can see. We'd need a bigger map to know just where it ends. It's incredible that something so enormous was hiding just behind the dusty curtain of the Milky Way's center.
So why do we care about these huge walls of galaxies beside the fact we love big things in space and we love breaking records? Well, according to the cosmological principle, all matter in the universe when viewed on a large enough scale should appear more or less uniform, and the largest structures shouldn't exceed 1.2 billion light years across. This is based on a mathematical theory put forth by none other than Isaac Newton. A possible galactic wall measuring over 1.2 billion light years across would mean our understanding of the universe is incomplete or perhaps incorrect, and there are even clues that there are even bigger structures out there.
Already in 1991, they found the Close Campusano quasar group, which is a collection of 34 quasars about 9.5 billion light-years away from us, and it extends over 2 billion light-years, clearly too large to be compatible with the prediction from the concordance model. Then there's the huge quasar group, which is huge. It spans a whopping 4 billion light-years.
In 2013, astronomers reported that they'd found what was, at the time, the biggest thing in the known universe. It's a collection of quasars about 9 billion light-years away, appropriately named the Huge Large Quasar Group. And some scientists say that it's impossibly big. Like 3 times larger than anything that could ever exist in our universe. When you look up at the night sky, it probably looks like there are about the same number of stars in all directions. Sure, some regions are a little denser or a little sparser, but in theory, you could divide the sky into squares so that each square had about the same number of stars in it. The cosmological principle applies that idea to the whole universe. If you broke the universe up into big enough cubes, each of those cubes would have about the same amount of matter in it. Mathematicians have used the cosmological principle to predict that there shouldn't be any collections of matter, or spaces between matter, bigger than about 1.5 billion light-years wide. So if you made your cubes with sides 1.5 billion light-years long, they should have about the same amount of matter in them. And for the most part, this seems to be true. Galaxies tend to be grouped together into structures smaller than about 500 million light-years. So everything seemed to line up. Mathematicians said there shouldn't be anything bigger than one of those cubes, because otherwise they would look different than the rest, and astronomers hadn't seen anything that big. But in the 1980s, astronomers started conducting surveys of quasars. By looking at where quasars were, they could get an idea of how galaxies in the early universe were spread out. And they noticed that quasars were often bunched together, just like galaxies are today, into what are known as large quasar groups, or LQGs. Some researchers think that these LQGs could be the roots of today's superclusters, which can contain thousands of galaxies. Large quasar groups could have anywhere between 2 and 20 quasars in them, and they could be up to hundreds of millions of light-years across. And in the 1990s and early 2000s, a couple of LQGs were discovered that were about 2 billion light-years wide, making them a little bit bigger than the limit imposed by the cosmological principle. Then, in January 2013, astronomers announced they'd found the Huge Large Quasar Group, or Huge LQG. Its 73 quasars are an average of 9 billion light-years away. And it's raised a lot of eyebrows, because it's a whopping 4 billion light-years across. That's 3 times larger than mathematicians said anything in the universe could get. Some scientists think that the discovery of the Huge LQG means that there really is some large-scale structure in the universe that we can't ignore any longer. Astronomers might have already found something much bigger than the Huge LQG, something called the Hercules Corona Borealis Wall, a group of galaxies that was discovered just a few months after the Huge LQG, and it might be twice as big.
In November 2013, astronomers found an enormously large structure, the largest in the known universe. It would take you 10 billion light-years to cross it. Astronomers call this structure Hercules Corona Borealis Great Wall. It lies in a distant part of the universe. This giant structure is a galactic filament, a vast group of galaxies bound together by gravity. This structure beats the previous record holder, the Huge LQG, or Large Quasar Group, which is a cluster of 73 quasars. Hercules Corona Borealis Great Wall is more than double the size of the Large Quasar Group, which spans about 4 billion light-years. Currently, astronomers are baffled because they don't have an idea of how something that big could have evolved.
And just in July, Alexia Lopez discovered the Giant Arc, a collection of galaxies, galaxy clusters, gas and dust that spans 3 billion light-years.
When we look up at the sky, we are treated to a cosmic view complete with clusters of stars and planets. But 9.2 billion light years away, beyond the view of the naked eye, astronomers have now detected a near-symmetrical cluster of galaxies. They're calling it the Giant Arc. That's because it's 3.3 billion light years across, connected by a cosmic web of dark matter, and it breaks what was thought to be the theoretical limit for how large these mysterious cosmic superstructures could be. Alexia Lopez, one of the astronomers at the University of Lancashire in the UK, who discovered the Giant Arc, had this to say about it. According to cosmologists, the current theoretical limit is calculated to be 1.2 billion light years across, which makes the Giant Arc almost 3 times larger. Can the standard model of cosmology account for these huge structures in the universe as just rare flukes, or is there more to it than that? Meaning, as we find more and more of these galactic arcs, of which astronomers have found about 5 others, at what point do we need to rethink our current models? In fact, the Giant Arc isn't even the biggest discovered so far. That honor goes to the Hercules Corona Borealis Great Wall, which could be as large as 10 billion light years across.
Theoretically, these structures shouldn't exist. It can happen that such clumps appear coincidentally in the concordance model. That's because this model uses an initial distribution of matter in the early universe with random fluctuations. So it could happen that you end up with a big clump somewhere just by chance. But you can calculate the probability for that to happen. The Giant Arc alone has a probability of less than 1 in 100,000 to have come about by chance. And that doesn't factor in all the other big structures. What does it mean? It means the evidence is mounting that the cosmological principle is a bad assumption to develop a model for the entire universe, and it probably has to go. It increasingly looks like we live in a region in the universe that happens to have a significantly lower density than the average in the visible universe. This area of underdensity which we live in has been called the local hole, and it has a diameter of at least 600 million light-years. This is the finding of a recent paper by a group of astrophysicists from Durham in the UK. They also point out that if we live in a local hole, then this means that the local value of the Hubble rate must be corrected down. This would be good news, because currently measurements for the local value of the Hubble rate are in conflict with the value from the early universe. And that discrepancy has been one of the biggest headaches in cosmology in the past years. Giving up the cosmological principle could solve that problem. However, the finding in that paper from the Durham group is only a mild tension with the concordance model at about 3 sigma, which is not highly statistically significant. But Zarkar and his group had another paper recently in which they do a consistency check on the concordance model and find a conflict at 4.9 sigma. That's a less than 1 in a million chance for it to be coincidence. This works as follows. If we measure the temperature of the cosmic microwave background, it appears hotter into the direction into which we move. This gives rise to the so-called CMB dipole. You can measure this dipole. You can also measure the dipole by inferring our motion from the observations of quasars. If the concordance model was right, the direction and magnitude of these 2 dipoles should be the same. But they are not. You see this in this figure from Zarkar's paper. The star is the location of the CMB dipole, the triangle that of the quasar dipole. In this figure, you see how far away from the CMB expectation the quasar result is. These recent developments make me think that in the next 10 years or so, we will see a major paradigm shift in cosmology, where the current standard model will be replaced with another one. Just what the new model will be and if it will still have dark energy, I don't know. But I'll keep you up to date, so don't forget to subscribe. See you next week.